Welcome to this explainer. Today, we are diving into a seriously fascinating engineering paper from the Kharkiv Aviation Institute. We're going to explore exactly how engineers are taking completely worn out, damaged physical aircraft parts and mathematically transforming them into pristine digital blueprints, just begging to be 3D printed. Honestly, it is an absolute masterclass in mathematical reconstruction, and it's a real game changer for the aerospace world. So here is our flight plan for today. We're going to cover 5 main areas. First, the aviation parts crisis. Second, the fundamental problem with 3D scanning. Third, how we actually reconstruct that original blueprint. Fourth, we'll look at the ultimate stress test with the impeller experiment. And finally, 3D printing the actual solution. Let's see how engineers are turning a major supply crisis into a highly innovative workflow to get safe planes right back in the sky. Starting right off with part 1, the aviation parts crisis. We really have to start with the high stakes here because they are massive. The Ukrainian aviation industry is currently facing a hyper-urgent need to rapidly restore aircraft operational readiness, right? But they are dealing with very limited access to spare parts, missing original blueprints, and totally restricted manufacturing capacities. Think about parts like impellers, compressor blades, or turbine blades. These things operate under absolute extreme mechanical and thermal loads. So because of those extreme environments, they suffer intense wear, localized damage, and even plastic deformation, which is basically permanent warping. And when these complex parts warp or wear down, immediate reuse is completely off the table. You literally cannot just put a compromised, warped part back into a jet engine. The whole system is grounded. This puts engineers between a rock and a hard place. On one side, you've got traditional manufacturing. It relies on lengthy manual measurements, drawing up completely new blueprints from scratch, and building highly specific tooling. It's built for mass production, so it is way, way too slow and just totally inefficient for single unit or small batch repairs. On the flip side, you have standard reverse engineering using a 3D scanner. Sure, it's fast, but it has one massive flaw. It only reproduces the exact physical state of the worn part. It's kind of like photocopying a crumpled piece of paper, you know? It just perfectly copies the damage instead of restoring the original clean design. Which leads us directly into the second big hurdle, the 3D scanning problem. The crux of the issue is that just pointing a scanner at a worn part simply isn't enough, especially with the complex curves of aircraft components. Aviation parts heavily rely on these intricate double-curved surfaces. When you try to 3D scan those shapes, you hit a major physical roadblock known as shadow zones. Basically, these are areas where the geometric information is completely lost because the scanner's laser is blocked by the part's own curves. It's like trying to shine a flashlight into a twisted pipe. The light just can't reach certain crevices, leading to blank spots and totally empty gaps in the digital data. The researchers hit the nail on the head here, noting that most existing approaches essentially just reproduce the current state of a worn or deformed part without ensuring the reconstruction of its nominal geometry. Now, nominal geometry is just the engineering term for the perfect, pristine, factory-fresh blueprint design. If you attempt to 3D print a part that has missing data from shadow zones or one that has physical wear and tear baked right into the file, you get an incomplete, structurally flawed component. And in the aerospace industry, where precision is literally a matter of life and death, an inaccurate digital model is absolutely useless. All right, so how do they fix this? Let's get into section 3, reconstructing the original blueprint. To solve this massive data gap, the researchers developed a genuinely incredible new methodology to mathematically reconstruct the past. They outlined 4 key steps. Step 1 is multi-iterative 3D scanning. Step 2, point cloud processing. Step 3 is high-density polygonal modeling. And Step 4 is parametric CAD reconstruction. By linking these steps together, engineers can take a physical, busted-up object and seamlessly transition it into a highly intelligent, flawless digital model. Let's break down exactly what that looks like. It all starts with solving those pesky shadow zones. Instead of just doing one quick pass with a laser scanner, the engineers use what they call multi-iterative scanning. All this means is that they deliberately change the spatial orientation and position of the part multiple times while scanning. By constantly flipping and reorienting the object, the laser can peek into those hard-to-reach curved areas from dozens of different angles. This brilliant little technique completely eliminates the shadow zones, making sure the resulting data cloud is incredibly dense and captures every single surviving millimeter of the part. Once they have that super dense complete scan, they move on to the magic of parametric CAD modeling. Remember, we absolutely do not want to copy the damage. So instead of leaving a dent or worn edge in the digital model, the software uses surface interpolation to mathematically repaint the missing fragments. It deeply analyzes the surviving sections, or uses the part's natural symmetry to extrapolate exactly what the missing piece should look like. It's literally like mathematically repainting the torn pieces of an old photograph so it looks brand new. It guarantees a continuous, smooth surface that perfectly matches the original nominal geometry.
Moving right along to Section 4, the impellers experiment.
Now, theory and software are great, but if you want to get actual human beings safely flying in the sky, you have to prove this works in the real world. So the researchers chose one of the absolute most complex parts of an aircraft engine to test their workflow, the impeller. The impeller has these wild, complex three-dimensional blades and intricate double-curved surfaces. They picked it precisely because it strictly demands extreme geometric accuracy. Even the tiniest, almost invisible deviation in the shape of an impeller blade will completely ruin the aerodynamic efficiency of the entire engine. It's basically the ultimate stress test.
So they put a heavily worn impeller through their multi-iterative scanning process and mathematically reconstructed its perfect shape. The results? Well, the reconstructed digital model was accurate to within an astonishing plus or minus 0.05 millimeters. Let that sink in for a second. We are talking about microscopic levels of precision, purely mathematically derived from a worn-out physical scrap of metal. The researchers did note that the largest deviations popped up in areas of really high surface curvature. But, and this is the absolute crucial takeaway, even those maximum deviations stayed strictly within the permissible tolerances required for the aerospace industry. This extreme precision proved that the whole methodology wasn't just some fun academic exercise in a lab. It actively produced a flawless, manufacturing-ready blueprint that engineers could actually trust.
And finally, we hit Section 5, 3D printing the solution.
With the perfect digital blueprint fully restored, we arrive at the physical manufacturing phase. Additive manufacturing, or 3D printing, has incredibly strict rules, especially when it comes to aviation. You can't just hit print. The digital model must have perfectly closed, continuous surfaces, zero self-intersections, absolutely no polygon mesh defects. It has to perfectly meet the specified geometric tolerances, and it must ensure the physical material layers will form correctly during the actual print. And because of the incredible CAD reconstruction we just walked through, their digital model checked every single one of these boxes flawlessly. This final step really reveals why this whole meticulous process matters so much. As the paper points out, any geometric errors or shadow zones from the scanning state don't just stay the same, they actually snowball and accumulate during the physical 3D printing process. By mathematically fixing the photocopy before hitting print, by fully restoring the true nominal blueprint, engineers guarantee they aren't printing a dangerously flawed part. This whole integrated workflow allows for small batch, rapid replacements that are structurally sound and ready for the skies. This is just a brilliant breakthrough in aviation manufacturing, born entirely out of necessity. But honestly, it leaves us with a really powerful question. If we can mathematically reconstruct the past to perfectly print the future, what else in our physical world is just sitting there waiting to be reverse engineered? Think about how these exact same principles of intelligent reconstruction could solve massive supply chain crises in the medical field, in the automotive sector, or even out in space exploration. It is a totally new way of looking at the broken things around us. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.